We have seen that in the classical case, you need 2 to the power of n minus 1 plus 1 attempts to determine whether a function is constant or balanced. So now I want to explain why the Deutsch-Jozsa algorithm can solve this with just a single query. In other words, instead of needing 2 to the power of n minus 1 plus 1 tries, we only need 1. To understand how this is possible, we first need to clarify a few basic concepts. As mentioned earlier, this video is intended for everyone, not just for people who already have a background in this topic. So let's go through some key ideas step by step. First, what is a qubit? A qubit is a quantum version of a classical bit. In classical computing, a bit can be either 0 or 1. For example, you can imagine a light switch. When the circuit is open, it's off. That's a 0. And when the circuit is closed and current flows, that's a 1. A qubit also has the states 0 and 1, but with one major difference, and this is the first essential property of quantum mechanics that we use in quantum computing, and that is superposition. So superposition means that a qubit can be in both states, 0 and 1, at the same time. That's not something we can really imagine because it goes beyond our everyday experience, but within the framework of quantum mechanics, it works incredibly well. It allows us to make extremely accurate predictions, and for that reason, we accept that this is how nature behaves at the quantum level. To make it more concrete, in a classical system, we can think of a transistor that either conducts or doesn't conduct electricity. A qubit, on the other hand, can be physically realized in various ways. So one intuitive way is in photonics, where we use photons, so these are particles of light, as qubits. Imagine we have two optical fibers. If the photon travels through fiber 1, we say it's in state 0. If it goes through fiber 2, it's in state 1. That's an easy way to picture how 0 and 1 can be represented. That's how qubits can be implemented in photonic systems. But there are many other ways to realize qubits. If you're curious, you can look it up or ask an AI to explain the different physical implementations. Now let's talk about the Hadamard gate. The Hadamard gate is the tool that creates superposition. So it doesn't matter how it's implemented in hardware. What's important is what it does to our qubit. When we apply the Hadamard gate to a qubit, it puts it into a superposition. Let's assume our qubit is initially in state 0, which is usually the case. When we apply the Hadamard gate to it, the resulting state is a superposition of 0 and 1. So mathematically, we write this state as 1 divided by the square root of 2 times the sum of 0 and 1. This factor, 1 divided by the square root of 2, ensures that the total probability remains 100%, because we are dealing here with probabilities. So in other words, if we measure the qubit now, there's a 50% chance of finding it in state 0 and a 50% chance of finding it in state 1. If the qubit was in state 1 before we applied the Hadamard gate, the result is very similar. We still get a 50-50 chance of measuring 0 or 1, but this time there is a minus sign in front of the 1. So instead of 0 plus 1, it becomes 0 minus 1. At this point, it's not necessary to fully understand where this minus sign comes from. What it means is that the phase of the quantum state is flipped. This will become important later, and I'll say more about it then. For now, it's enough to understand the key idea. Whether we apply the Hadamard gate to a 0 or a 1, we end up with a superposition in which both outcomes are equally likely when measured. The only difference is that we have a minus sign in the second case. And just one more important point. This superposition exists only as long as we don't measure the qubit. As soon as we perform a measurement, for example, by placing a detector at the end of both optical fibers, the superposition collapses. That detector will register whether the photon is in fiber 1 or 2, and from that point on, the system is in a definite state again, either 0 or 1. So if you place the detector at fiber 1 and it clicks, the photon was in fiber 1. If it doesn't click there, then it was in fiber 2. That's what we mean by measurement. So again, when the Hadamard gate acts on a 0 state, the result is an equal mix of 0 and 1. And when it acts on a 1 state, we also get an equal mix, but with a minus sign in front of the 1. This minus sign reflects a phase difference, and even though we won't go into detail now, it's something we need to include in the model. So because later it will lead to different outcomes, and that's what gives the quantum algorithm its power. So if you're interested, you can explore this further, but for now it's not essential to understand it in full detail in order to follow the core idea. Before we continue, I just want to say you don't need to understand every technical detail I'm about to explain. What matters is that you get a general idea that will be more than enough to follow the rest of the video later on. So let's start with the X gate. The X gate flips the state of a qubit, and if the qubit is in state 0, it becomes 1. If it's in state 1, it becomes 0. It's very simple. Next is the oracle, which we usually write as U sub f. This represents the function of f of x, the one we're trying to analyze. So the oracle is basically a black box that gets inserted into our quantum circuit. We don't know exactly how it works on the inside, but we do know that it takes the input qubits, performs some internal computation based on f of x, and encodes the result into the output qubit. It's important to understand that the oracle doesn't return a value in a classical sense. It doesn't print out the result. Instead, it changes the state of a qubit in the system depending on the value of f of x. So when I say we apply the oracle, I mean that this function f of x is now embedded in our quantum circuit and becomes part of the overall operation. And finally, we have the tensor product. That's the little x with a circle around it. It's a mathematical operation we use in quantum mechanics to combine multiple qubits into a single joint quantum state. So here's the basic idea. Let's say I have two qubits. One is in some state, for example 0, and the other is in another state, for example 1. When I combine them using the tensor product, I get a new state that represents both qubits together. We write this as 0, 1, and it describes the full two-qubit system. If both qubits are in superposition, then their tensor product includes all possible combinations of the individual states. So we end up with a superposition of 4 states, 0, 0, 0, 1, 1, 0, and 1, 1, all happening at the same time. That's one of the key ideas behind quantum computing. We can represent many possible inputs in parallel within a single quantum state. Again, don't worry about fully understanding the math behind this right now. Later in the video, when we do actual calculations, I will explain everything step by step. For now, just remember, the tensor product is how we describe systems that contain more than one qubit. Before we begin with the actual calculations, I'll briefly outline the steps we're about to take. We will now build the quantum circuit step by step, and I will explain what's happening mathematically at each stage. In the end, we will perform a measurement, but not on the output qubit. We will measure only the input qubits to find out what state they are in. The result will be the following. If the function is constant, we will always measure the input qubits in the state 0. So if we assume we have two input qubits, then 0, 0. If the function is balanced, we will always measure some other combination. For example, 0, 1, 1, 0, or 1, 1. This means that with just a single measurement on the input qubits, we can immediately determine whether the function was constant or balanced. Now let's go through the steps of the algorithm. So step 1, we initialize n input qubits in state 0. Using our photonics analogy, this would mean placing the photon into the first rail, which represents the 0 state. Step 2, we set the output qubit to state 1. Why we do this will become clear later from the math, but for now we simply set the output qubit to 1. Step 3, we apply Hadamard gates to all qubits, both input and output. This puts every qubit into a superposition. Step 4, we apply the oracle, which encodes the function f of x into the quantum circuit. Step 5, we apply another round of Hadamard gates, but this time only to the input qubits, not to the output qubit. And the final step, step 6, we measure the input qubits. Based on the result, we can immediately decide whether the function is constant or balanced with just one run of the algorithm. With step 1, the initialization of the input qubits. So from now on, I will describe the overall quantum state, meaning the state of all input qubits and the output qubit together, using the Greek letter psi. For each step of the algorithm, I will give this state a number. So after the first step, I refer to it as state C1, which means the full quantum state after step 1. At this point, all input qubits are initialized in state 0. I describe this as a 0 tensor product n times. That simply means we are combining n qubits, each in the state 0, using the tensor product. In words, 0, tensor product, 0, tensor product, 0, and so on. 1 0 for each of the input qubits. But we also have the output qubit, which is part of the system 2. So right now it is also in the state 0. So we add one more tensor product followed by another 0, and this last 0 stands for the output qubit. I write this last 0 separately to make it clear that it belongs to the output qubit and not to the input qubits. So the full quantum state, which are now called C1, consists of n input qubits, each in the state 0, joined together using the tensor product, and one output qubit, also in the state 0, added at the end using another tensor product. That is the initial state of the entire quantum state after step 1. Now we apply an X gate to flip the output qubit from 0 to 1. As mentioned earlier, when you apply an X gate to a qubit in state 0, the result is state 1. That's exactly what we're doing here, and I'll also show this step again in mathematical form. So what does our total quantum state look like after this operation? The input qubits remain unchanged. They're still all in state 0, just like before, but now the output qubit is in state 1 because we applied the X gate to it. This means all input qubits are still in state 0, and the output qubit is now in state 1. That completes step 2. Now we move on to step 3, where we apply Hadamard gates to all qubits in the system. We now label the full quantum state psi3, and we apply a Hadamard gate to each of the input qubits, and we also apply a Hadamard gate to the output qubit. So we write C3 equals Hadamard on the input qubits, tensor product with Hadamard on the output qubit, applied to the previous state C2. Let me explain what that means. We apply a Hadamard gate to each of the input qubits, and all of those qubits are still in state 0 from the previous step. So we apply n Hadamard gates, 1 to each 0. If we write this out in words, we have Hadamard on 0, tensor product with Hadamard on 0, and so on. 1 for each input qubit. Now remember, applying a Hadamard gate to 0 gives a superposition, 1 divided by the square root of 2 times 0 plus 1. So for two input qubits, the result is 1 divided by the square root of 2 times 0 plus 1, tensor product with 1 divided by the square root of 2 times 0 plus 1. If we multiply those together as required by the tensor product, we get 1 divided by 2 times the sum of 0, 0, 0, 1, 1, 0, and 1, 1. That's a superposition over all possible combinations of the two input qubits. We can now write this more compactly using summation notation. The state of the input qubit is 1 divided by the square root of 2 to the power of n times the sum over x from x equals 0 to the power of n minus 1 of the state x. So let's look at a concrete example. If n equals 2, then 2 to the power of 2 is 4. So we sum from x equals 0 to x equals 3. And these values correspond to x equals 0, state 0, 0. X equals 1, state 0, 1. X equals 2, state 1, 0. And x equals 3, state 1, 1. So we get 1 divided by 2 times 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And this is exactly the full superposition of all possible input states for n equals 2. Now let's look at the output qubit. So far, we've only looked at the effect of the Hadamard gates on the input qubits, but we also need to apply a Hadamard gate to the output qubit, which was in state 1. As we discussed earlier, applying a Hadamard gate to state 1 gives 1 divided by the square root of 2 times 0 minus 1. Now we combine this with the superposition we just created on the input side. So the full quantum state after step 3, which we call C3, is 1 divided by the square root of 2 to the power of n times the sum over x from x equals 0 to the power of n minus 1 of the state x and tensor product with 1 divided by the square root of 2 times 0 minus 1. To summarize, the input qubits are now in a uniform superposition of all possible combinations. The output qubit is in a balanced superposition with a negative sign, so 0 minus 1, and the overall system is described by the tensor product of these two components. That is the complete quantum state after applying all Hadamard gates to both input and output qubits. Move on to step 4, where we apply the oracle. This is the unitary operation U sub f to our quantum circuit. We write this as U sub f applied to C3, meaning we now apply the oracle to the entire quantum state we had at the end of the previous step. What the oracle does is the following. It calculates the function f of x and then applies that result to the output qubit using a gate known as the XOR gate. In circuit diagrams, the XOR gate is usually represented by a plus sign with a circle around it. I won't go into the mathematical details of how this works. It's not too complicated, but it would take up too much time in this video. So what's important to understand is just this. The function f of x returns either 0 or 1. If f of x is 0, the output remains unchanged. And if f of x is 1, the output qubit is flipped. But here's the interesting part. Because the output qubit is already in a superposition, specifically 0 minus 1, flipping the output qubit actually leads to phase flip. This means that the entire superposition gets multiplied by minus 1. We represent that with the expression minus 1 to the power of f of x times the original superposition state of the output qubit. Let me explain that more clearly. If f of x is 0, then minus 1 to the power of 0 is just 1, so nothing changes. If f of x is 1, then minus 1 to the power of 1 is minus 1, and the sign of the entire state flips. So the key idea is, instead of modifying the output qubit directly, we now shift this phase factor into the input part of the state. So how does the full state look now? We define the new quantum state as psi4, and it looks like this. We take 1 divided by the square root of 2 to the power of n, then a sum over x from x equals 0 to 2 to the power of n minus 1. And for each x, we multiply the state x by minus 1 to the power of f of x. And finally, take the tensor product with the unchanged output qubit state, which is still 1 divided by the square root of 2 times 0 minus 1. Mathematically, we are allowed to move the phase factor into the input part of the state. This is just a reordering of the expression, and it's completely equivalent. So to summarize, the output qubit remains unchanged, but each input state x is now multiplied by a factor of minus 1 if f of x equals 1. That's all we need to know about the oracle step. Anyone who wants to understand more about the phase flip or XOR gates is welcome to explore it further or ask an AI assistant, for example. But for now, the key takeaway is this: f of x is encoded as a phase shift, and this shift appears in the input part of the state, while the output qubit stays the same. Let's move on to step 5, where we apply a second Hadamard gate, but this time only to the input qubits. We take the quantum state of the input qubits, and now we add the Hadamard gates that are applied again to each input qubit. That gives us the following expression. So the Hadamard gates in a tensor product with the state x result in the following expression: 1 divided by the square root of 2 to the power of n times the sum over c of minus 1 to the power of x dot c times the state c. How we arrive at this exact expression, I won't explain in detail here. It's not very difficult, but it would go beyond the scope of this video. So I'll leave it as it is. If you're interested in how to derive this exactly, you can ask an AI or just look it up on Google. Now, if we plug this expression back into the first line, we get the following result. And if we now rearrange things a little, we arrive at C5 equals the sum over C of 1 divided by 2 to the power of n times the sum over x of minus 1 to the power of f of x plus x dot c times the state c. For the final step, namely the measurement of the qubits. More precisely, we are measuring only the input qubits. These input qubits are currently in a superposition. This means that they simultaneously exist in all possible states. For example, with two qubits, the states are 0, 0, 0, 1, 1, 0, and 1, 1. As soon as we perform a measurement, the wave function collapses and we observe exactly one of these states as a result. The measurement itself is not deterministic. That means we cannot predict which state we will get. We can only calculate the probabilities for each possible outcome. The state we currently have, we call it psi5, is a sum over all possible states where each state has a certain amplitude. This amplitude is called alpha c. That means the state C5 is a superposition of all state C, with each state C weighted by its amplitude alpha c. Now let's look at how the amplitude is calculated. There's a term in the formula that looks like x times c, but this is not normal multiplication. Both x and c are bit strings, and this operation means we take the bits of x and c, multiply them pairwise, and then add them together using, for example, XOR. So the result is always either 0 or 1. Once we have the amplitude, we can calculate the actual measurement probability for a specific outcome by taking the absolute value of that amplitude and squaring it. Now let's look at a simple example. Suppose our function is constant and always returns 0. Then we try the bit string that is all zeros. So we have 0, 0, 0, and so on. And for this case, the special x times c operation always gives 0, and the function also gives 0. That means each term in the amplitude is just plus 1. We're adding up a bunch of ones, and since there are 2 to the power of n such terms, we divide by 2 to the power of n and get exactly 1. This means the amplitude is 1 and the square of 1 is still 1, so we get a 100% probability of measuring that all 0 state. So what we've just seen is that if the function is constant, we will always measure the bit string consisting only of zeros. That is, all input qubits will be 0 after the measurement. We already tried this for the case where the function always returns 0, but if the function always returns 1, the result is actually the same. The logic of the circuit ensures that the outcome will still be the all 0 bit string as long as the function is constant. Now one might ask, what happens if the function is balanced instead? Well, strictly speaking, we don't even need to calculate that because we already know if we don't measure the all 0 bit string, then the function cannot be constant. And since it's either constant or balanced, it must be balanced. So that's already enough to solve the problem. But just for completeness, let's briefly think about what would happen if we try again the all 0 bit string as output and assume the function is balanced. That means that for half of the input, the function returns 0, and for the other half, it returns 1. If we now plug that into the formula of the amplitude, we can split the sum into two parts, one for the terms where the function returns 0 and one where it returns 1. Each of these parts will cancel each other out, so the total result will be 0. That means the probability of measuring the all 0 bit string is exactly 0 if the function is balanced. In other words, if we get anything other than the 0 bit string, we know that the function must be balanced. So what we've shown is really powerful. With just one single measurement of input qubits, we can determine with certainty whether the function is constant or balanced. And with that, we are at the end of the Deutsch-Jozsa algorithm.